After years of research by countless physicists, we've uncovered something incredible about the fundamental makeup of the universe. It turns out that everything is constructed from a small set of building blocks called fundamental particles. These particles are subject to four fundamental forces, which we've been able to understand through the Standard Model of particle physics. This theory, which emerged in the 1970s, has been hugely successful in explaining experimental results and predicting a wide range of phenomena. Today, it stands as one of the most thoroughly tested physics theories in history. To understand this theory, let's start with the basics first. The Standard Model is a theory that describes three of the four fundamental forces of nature: the electromagnetic force, the strong nuclear force, and the weak nuclear force. It does not include the fourth fundamental force, gravity, which is described by the theory of general relativity. The Standard Model also describes the 17 known fundamental particles that make up matter. These particles are divided into two categories: fermions and bosons. Fermions are particles that make up matter, like electrons, quarks, and neutrinos. Bosons are particles that carry the fundamental forces, like photons, gluons, and W and Z bosons. One of the most important concepts in the Standard Model is the Higgs boson. The Higgs boson is a particle that gives mass to other particles. Without the Higgs boson, particles like electrons and quarks would be massless and would travel at the speed of light. The discovery of the Higgs boson was a major milestone in physics, and it confirmed the existence of the Higgs field, which is responsible for giving particles mass. Now, let's dive deeper into each of the three fundamental forces described by the Standard Model. The electromagnetic force is responsible for the interaction between charged particles, such as electrons and protons. This force is described by the theory of electromagnetism, which was first proposed by James Clerk Maxwell in the 19th century. The theory of electromagnetism describes the behavior of electric and magnetic fields, and how they interact with charged particles. The strong nuclear force is responsible for holding the nucleus of an atom together. This force is described by the theory of quantum chromodynamics. QCD describes the interaction between quarks, which are the particles that make up protons and neutrons. The strong nuclear force is mediated by particles called gluons. They bind quarks together to form protons and neutrons, which are the building blocks of atomic nuclei. Without the strong nuclear force, atoms would not be stable and the universe as we know it would not exist. The weak nuclear force is responsible for certain types of radioactive decay. This force is described by the theory of electroweak interaction, which was developed in the 1970s by Sheldon Glashow, Abdus Salam, and Steven Weinberg. The theory of electroweak interaction describes how the weak nuclear force and the electromagnetic force are related. Now, let's talk about some of the latest developments in the Standard Model. One of the biggest challenges in the Standard Model is the hierarchy problem. The hierarchy problem refers to the large difference in energy scales between the weak nuclear force and gravity. In the Standard Model, the energy scale of the weak nuclear force is much smaller than the energy scale of gravity. This means that there must be some unknown mechanism that keeps the two scales separate. Many physicists believe that this mechanism could be related to the discovery of supersymmetry. Supersymmetry is a theoretical concept that predicts the existence of a new set of particles that are related to the particles in the Standard Model. These particles are known as supersymmetric particles, or sparticles. Supersymmetry would provide a natural explanation for the hierarchy problem, as it would introduce a new symmetry between fermions and bosons. Another recent development in the Standard Model is the discovery of neutrino oscillation. Neutrinos are particles that have no electric charge and very little mass. Neutrino oscillation refers to the phenomenon where neutrinos change from one flavor to another as they travel through space. There are three known types, or flavors, of neutrinos called electron, muon, and tau neutrinos. As neutrinos travel through space, they can undergo quantum mechanical interference, causing them to change their flavor. This means that a neutrino that was initially produced as an electron neutrino can change into a muon or tau neutrino, and vice versa. This discovery was made in the late 1990s and early 2000s, and it confirmed the existence of neutrino masses, which were not predicted by the Standard Model. The discovery of neutrino oscillation has led to further research into the properties of neutrinos, including their mass hierarchy and whether or not they violate a fundamental law of physics known as CP symmetry. These questions are being studied by a number of experimental collaborations around the world. In addition to these developments, there are also ongoing efforts to unify the forces described by the Standard Model with gravity. This is known as the problem of quantum gravity, and it remains one of the biggest challenges in physics. Many physicists believe that a theory of quantum gravity will require the development of a new theoretical framework that goes beyond the Standard Model. Overall, the Standard Model is an incredibly successful theory that has been rigorously tested through experiments and observations. However, there are still many questions that remain unanswered, and the search for new physics beyond the Standard Model continues. So, that was all for this video. I hope it has given you a better understanding of the Standard Model and its place in our current understanding of the universe, and as always, do subscribe to our channel and thank you for watching.